Here we have an RL circuit with sources and resistors and a single inductor. Our first step is to find the initial current through the inductor. We're told that the switch has been closed for a long time, so we want to draw that circuit the way that it is before the change is made to the circuit. So this is our circuit. Note that I've reversed the position of the inductor and that 2 ohm resistor. They're still in parallel, so it doesn't change the circuit at all, but what it's doing for us is it really gives us a break between the inductor on one side and the circuit that's connected to it on the other side. We want to find the current passing through that inductor before the switch is thrown. So the switch has not been thrown yet, so we can treat it there like it's a short circuit or a piece of wire. And what we'll want to do is find the Norton equivalent of what the inductor is connected to. And so giving us this breaking point is a nice way to be able to just remove the inductor that we have here and find the Norton equivalent circuit between these two terminals. So if we're trying to find a Norton equivalent circuit, the first thing we're going to do is look for the short circuit current that's going to give us our Norton source current. Notice right here, this 2 ohm resistor is being shorted out by that short circuit, so that's just going to go away completely. Notice that the 6 ohm resistor and the 30 ohm resistor are in parallel with one another. I have a voltage source here. I'm looking for a current. I have these guys in parallel, but they're in series with that resistor, so what I'm going to do is do a source transformation to convert this into a current source, which leans towards us having the short circuit current, and the source transformation will give us a parallel resistor to combine with other parallel resistors. Notice here that the current from the source is going to split among these 3 different resistors that are all in parallel to one another, and that whatever current is going through the 6 ohm resistor, that's going to be the current going through the short circuit. So we're going to use a current divider here to find the current through the 6 ohm resistor, which is ISC. So I've found the current going through the 6 ohm resistor, and thus the short circuit current. So I've got 12.5 amps flowing down through that as the Norton source current for the Norton equivalent circuit that we have here. That's going to be the initial current through our inductor. The only thing to notice here is that we assume that the current's flowing downwards. I is given as flowing upwards, and so for the first question we're being asked, the initial value of I, this current is flowing in the opposite direction from what it should be. So when we report that value, we're going to go ahead and give it a negative value in order to show that it's flowing the opposite direction from how we defined it. And we'll go ahead and write that over there. If we want to find the initial energy stored in the inductor, there's an equation for that as well. Since we know the inductance of the inductor, that's a given amount, we know the initial current flowing through it, we can find the energy stored in that inductor. And so we can plug in those values and find an initial energy for the inductor as well. When we start being asked about the time constant of the circuit for t is greater than 0, the switch is opening at t equals 0, so if we want to look at times after that, we need to look at the circuit with the switch open. If the switch is open, that means that all of this circuit over here is going to be eliminated, and that the only thing that we're going to care about is this part of the circuit. That's where our inductor is, and that's where the interesting behavior is going to be. So we need to focus on this part of the circuit. So what let's do is redraw what we've got, focusing on this part of the circuit, and we'll be able to finish the rest of the problem. So we have our new circuit that's been isolated by that open switch. We have the inductor and the current through the inductor. Once the switch is thrown, that current is going to be continuous, so we're going to have the same current the instant after the switch is thrown and the inductor is isolated. But as the inductor continues to drive that circuit, it will deplete its energy and that current will fall off. If we want to find the time constant of the circuit, we have an equation for the time constant, and we know what the inductance is and we know what the resistance is. In this case, there's only one resistor that's left connected to the inductor, so that'll be the resistance that we'll use. And so we find that the time constant tau of this circuit is going to be 4 milliseconds. Then we're asked to find the numerical expression for I, the current through the inductor, and we have an equation for that as well for the natural response. That's the natural decay of an inductor that's charged and allowed to discharge across a single resistor like we have here. So we'll look at that equation first. So we start with the equation for the inductor current. We know the initial value of the current through the inductor. We know tau, the time constant. We can plug those values in to get the inductor current as a function of time. And then finally, we're asked about the energy that's stored in the inductor and how much of that's been dissipated by that 2 ohm resistor. So we found an equation for the energy dissipated by a resistor connected to a discharging inductor, and this is that equation. So we know the initial value stored in the inductor. That's this amount right there. And as time goes on, more and more energy is dissipated by that resistor. So after 5 seconds have elapsed, that means that our time then is 5 milliseconds, and we want to know how much energy has been dissipated at 5 milliseconds, so we can plug in and figure out what that is. And so we find this number here. This is the amount of energy that's been dissipated by the resistor. So this is how much has been dissipated. This much here was how much there was to begin with. So the percentage that has been dissipated is going to be how much has been dissipated divided by the total amount that is there, and that comes out to be about 92% has been dissipated. So the energy goes away pretty quickly.